right, let's get started for today. A couple of announcements. Your homework 3 on games is out. It's due next week, exceptionally on Tuesday because of President's Day on Monday, so you get an extra day. Your Project 2 Multi-Agent Pac-Man is also been released. It's due next week, Friday at 5. There will again be an optional mini contest. This contest is, your submissions for this contest are due on Sunday at midnight after the Friday when the project is due. Any questions about logistics? All right, let's start with some AI in the news. So this is from about a year ago, but very relevant for what we're going to be covering in the next few lectures. So I want to bring it up here. So has anybody heard of Nest? Nest thermostats, Nest fire alarms and so forth? Yes. So about a year ago, Nest got acquired by Google for $3.2 billion. And the main product they had at the time, and probably still, is the learning thermostat. So it's a thermostat that learns to adapt to what's going on in the place it's installed in. And that way might save money in terms of how much is spent on heating when you might not even be there, or might just make you more comfortable than it would be without this kind of learning thermostat. The kind of learning that you could apply to build a smart thermostat is what we'll be covering in the next 4 lectures. So we'll get back to this after those 4 lectures. Now, of course, they haven't said what's inside there, but we can hypothesize of the type of system that could be inside there once we're through the next 4 lectures. Okay, so today we're going to look at Markov decision processes. Next lecture will be a lecture 2 on Markov decision processes, and then the 2 lectures after that will be reinforcement learning, which will also use the Markov decision process framework, but we'll look at learning within that framework. So the problem we're trying to solve is the problem of non-deterministic search. So imagine you're trying to get some rewards, maybe a beautiful blue diamond, but the world is non-deterministic, and as you try to find your way to your rewards, there might be fire pits that you really don't want to fall into, but due to stochasticity of how things work, if you get too close, maybe you might fall into those pits by mistake, or intentionally if you are making a bad decision. Okay, so our running example is going to be this Gridworld over here. Keep in mind that it's not about solving 4x3 grid worlds. This is just an example that allows us to illustrate the point, but MDPs in general will be a lot larger than MDPs with just 12 states. So it's a maze-like problem in our running example. There's a wall here which blocks that square. Movement is noisy, which means when the agent tries to move in any given direction, there is a chance that they actually move in a different direction. So the action north results in 80% of the time indeed moving north in this example, but 10% of the time instead the engine would move east, and 10% of the time the engine would move west. Not intentionally, but just because of the noise in the system. If there is a wall and you try to move into a wall, you'll stay in place. So you can't, if you're here, you're allowed to take the action north, then 80% of the time that'll be successful. You'll bump into the wall and stay in place. 10% of the time you'll move west, 10% of the time you'll move east. Okay, so at each time step, we'll go from time step 0 to 1, 1 to 2, and so forth. There is a reward associated with the transition. So the agent will be in a state, decide on an action. There will be an outcome of that action, which is the new state of the agent, and associated with going from that current state, taking that current action, landing in a new state, there will be a reward. In this example, the reward, we call it a living reward, is a small negative value encouraging you to not just loiter around and just do useless actions. So anytime you're just kind of doing anything, you get a negative reward. But then there are big rewards here at the end. There's a reward of +1 if you reach this location and from there take the exit action. And so having this negative living reward encourages you to go there sooner rather than later. And then there's a very negative reward here. If you hit this state, you only have one action available, the exit action, and on taking that action, you'll get a reward of -1, which is the worst in this particular case. Okay, so the goal will be to maximize the sum of rewards that you accumulate over time. So let's look at this in the context of what we've seen so far. So if we had a deterministic grid world, we decided to take the action north, this here would be the result. On the other hand, in our current stochastic grid world, if we try to take the action north, sure, that might happen, maybe 80% of the time, but you could also end up in this state or in this state over here. So here's how we're going to formalize this. A Markov decision process, or an MDP, using the first letters of these words, is defined by a set of states, S, a set of actions that's available in those states, A. Then there's a transition function. This is a lot like the successor function we saw in earlier lectures. The transition function tells you for state S and an action A, the probability that you end up in state S prime. Another way to write this is like this: the probability of landing in state S prime given that you were in state S and took action A. We'll also refer to this as the model or the dynamics, because this is what governs how things change over time. There will also be a reward function, which associates a reward with every state action next state triple. Sometimes it's simpler, sometimes the reward will just depend on the state that you're in, or sometimes it will just depend on the state that you land in. But to be general, we'll work with equations that have a reward that depends on current state, current action, and next state that you land in. There's a start state, and then there is maybe a terminal state. Say maybe in search we always had terminal states where you meet the goal condition. In MDPs, that's not necessarily the case. We're often interested in acting in worlds where we'll be acting infinitely long, and you can keep collecting rewards over time, and there will not necessarily be a terminal state. In this example here, there are terminal states, and there's actually one, it's not shown here, but once you're in this state, and you take the one action available to you, which is the exit action, you land in a terminal state. Same thing here. You take the exit action, you land in a terminal state. And on this transition, there will be a reward of -1. On this transition, a reward of +1. So far, what we have here is a lot like what we looked at in Expectimax. In fact, any Expectimax problem you could define this way and the other way around. The reason we're defining it this way now is that this will give us a new tool to solve stochastic search problems. The reason we'd like to have a new tool is that it allows us to solve problems where you have an infinite horizon, so you're acting indefinitely long rather than just a finite amount of time. We'll also see that these tools that we'll look at today will allow us to deal with something that we haven't looked at yet in Expectimax. So if you think back to the second lecture, we looked at tree search. Then the third lecture, we looked at graph search. And graph search avoided repeated computation by not expanding states more than once. Now, imagine you have an Expectimax tree where some states appear many, many times. Expectimax is not taking advantage of that. The solution algorithms we'll see for MDPs are able to take advantage of that and avoid repeated computation for states that are repeat states. So we won't see an Expectimax graph search, but you can think of the algorithms that we're going to cover here as providing that type of functionality in the Expectimax setting. Okay, so let's take a look at a demo. So this is our grid world. Here is the reward of +1 if you exit from there, -1, agent starts over here. So on the keyboard I can choose actions. In this case I'm going to press the right arrow for east. Doesn't mean the dot will move east. Let's see what happens. 80% chance it will, but 20% chance it'll actually do something noisy and then somewhere else. So I press east. It actually took that action successfully. Now I'm pressing east again. It actually stayed in place, meaning that it veered noisily to the left or to the right, but there was a wall left and right of where it is, so it essentially stayed put. Take the action east again. Now let's take the action north. Noisily moved west. Let's take the action east, north, north, east. And here there's only one action available, which is the exit action. So take the exit action, collect the reward of 1, and that completed this episode. Now the whole system might reset, then you could play this again. So that's the world things are happening in. If we look at the console, we see that as we took actions, we were in some state 2-2, took the action east. This was the state we ended up in, 3-2. We got a reward of -0.1. That reward is the living reward. It's that reward that encourages us to collect that reward, since we want to maximize the sum of rewards, to encourage to get that good +1 at the top early on. A living reward of -1 will encourage you to get there as soon as possible. Okay, so let's go back to the slides. What is Markov about Markov decision processes? So what's this Markov thing doing in the name of what we're looking at? Markov was a statistician or mathematician from quite a while ago. In general, whenever you see his name appear, what it refers to is that given the present, nothing about the past can tell you anything about the future. And when I say given the present, it's whatever you define as your state, or in this case, state in action. So if you know your current state, your current action, whatever happened in the past is not going to give you any additional information about what the result will be of taking that action in your current state. So in general, if we had a general process, the distribution over what the state at time t+1 would depend on everything that happened before. But in a Markov decision process, all this stuff over here actually has no influence on the probability of landing in state S prime and starting from state ST, taking action AT. And so you can simplify it to this equation over here. This is a lot like search, where the successor function just depended on the current state in action, not on states and actions you've seen in the past or experienced in the past. Is every process that we encounter going to be a Markov process where this is true? It depends on how we define the state, right? The key here to get a Markov decision process is to define your state as all that information from the past in some sense summarized in some set of numbers that are now enough to be able to predict what's going to happen in the future stochastically, such that no other information from the past would have helped you. Sometimes it'll be an approximation, just like our search problems were approximations. You might just look at cities in a road network rather than looking at the details of how a car would move and so forth. And in that process, you might lose something. Same thing here, making something into an MDP, you might lose something, but hopefully it'd still be a good approximation of what it would be in the real world. Now, the naive way of making everything into an MDP would be to take your entire history and always say, my state is the entire history. And then it's always guaranteed to be an MDP, because then nothing about the entire history is going to help you beyond what's already in the state, because the entire history is already in the state. But doing that will prove not very efficient for any of the algorithms that we'll look at for solving Markov decision processes. So the reason to keep this state small is to keep the algorithms efficient when you're trying to solve them. So what we're after when solving a Markov decision process is a policy. So this is not exactly the same as what we were after before. So before, in our single agent search problems, we were looking for an optimal plan. An optimal plan was a sequence of actions that you would execute would be the right thing to do. But now we have stochasticity, and so we don't really know how things are going to play out. And just having a sequence of actions is not enough to then just execute and be happy with the outcome of that. You want a more sophisticated solution that tells you for every possible contingency that you could encounter what the right action would be. And that's a policy. Concretely, for this grid world, a policy would tell you for every state what action you would be taking. Expectamax, which we've looked at before, did not compute policies, right? It just computed the first action. What we'll look at now is something that will, for every possible state you might encounter, tell you what the right action would be. So let's take a look at optimal policies. Here is an example of our grid world, still with the +1 to exit over here, -1 to exit over here. The living reward is -0.01. So it's a pretty small penalty for taking longer. And so what we see here is that the optimal policy guides you from this square over here all the way around to the good exit square, because it has the time to do that. There's a very low penalty to take that time, and if you were instead to go this way, it could be more dangerous. You might not do as well. Now, there are a couple of subtle things to notice here. One interesting thing is that over here, it's taking the action into the wall. Why would that be? There. Exactly. The way the transitions are defined, the transition function is defined, is that 80% chance your action succeeds, which in this case would mean bump at that wall and stay put. 10% chance you veer off to the left, 10% chance you veer off to the right, but you never noisily move in the opposite direction of your action. And so with this action choice here, you would never move into the pit. It never happened. Now, it might take a long time before you actually move up, because you're never even really trying to move up. You only have a 10% chance of moving up. But when you are there, that's the safest thing to do. It's the thing that guarantees you you'd never fall into the pit. Now, if the living reward penalizes you a little more, you might not have that patience if you're over here, and you will try, the optimal thing will be to try to move up. Now, every now and then you will fall in the pit, but on average, it's the better action to take, because usually you will not fall in the pit, and you'll get the reward of +1 sooner, which will be good because you'll not be penalized as much along the way. Now, keep in mind, when you look at these maps, these are just policies that you could execute in those grid worlds. It doesn't mean that the agent would actually, when it starts here, follow this exact path. There is noise. The execution could look different from what it tries to do. In fact, often, at least in one of those states, something else will happen, because there's a 20% chance that noise kicks in and does something else than the action you wanted. If the living reward gets even more negative, so penalizes you more for taking time, then if you start over here, you'll hope for this way of exiting, taking more of a risk, because it's worth it, because you get penalized -0.4, which is a lot to get penalized on every step. And then if the living reward is very negative, you get the suicidal behavior, where even if you start over here, you don't try to move up, because living reward of -2 is really, really bad, and you don't want to move up and then another move to finally get the +1, and in the process encounter -2 multiple times. So the optimal policy will depend on how you define your reward function. So when we looked at utilities last time, effectively the utilities are sitting in the reward here. You define your utility function by defining rewards, and that defines what optimal behavior is for a rational agent. So let's take a look at another example. Here's a racing example. Let's say you're looking at a robot car and you want it to race, and there are 3 possible states. The car could be cool, warm, or overheated. The purpose of the game is to race, so to say, so you want to travel as far as possible, as quickly as possible. So you could be in any of those three states. The actions available to you are to either decide to move slow or move fast. Whenever you move fast, for example, shown over here, and well, it could go this way or this way, and here's another fast. Those are the red actions. Whenever you move fast and it's successful, meaning that you don't overheat your car, you'll get a positive reward of +2, which is the best you can get. If you move slow, you will get a +1, which is still reasonable, but not as good. Once you move fast and happen to hit the overheated state, you get a reward of -10, which is the worst thing. And once you're there, you're stuck. You stay there forever. Game is over. Okay. So you can see there's some subtlety here that you don't want to just move fast because you might get warm and then overheat it. You want to sometimes move slow, sometimes move fast, and we'll see what the optimal strategy is as we go along. But this is just a definition of the problem here. Okay, so we can build a search tree for this. Essentially, like an expected max tree, right? You start in the cool state, let's say. You could take one of two actions, slow or fast. When you take that action, there's a stochastic transition. The first case, when you're already in the cool state, you move slow. That stochastic transition is actually deterministic. You always stay cool. If you're moving fast, you can end up with a cool car or a warm car. Then next layer of actions, same thing happens. If you start warm, you could end up back into cool if you take the slow action, but you might stay warm, or you might end up this way and overheated, which means the game is over. So it's important to see the equivalence here, that we can look at this just as well as an MDP as we can look at this as an expected max problem. So MDPs are search trees. What's the exact equivalence here? So you might have some start state. You can take an action. After that, you hit a new type of state, which we'll call a Q state. That's where you hit a chance node. You've committed to your action in the current state, but nature hasn't yet told you what the outcome is going to be. Then nature kicks in, rolls the dice for you, and you get an outcome, any of these possible successor states, and then this process repeats. The thing that happens over here is essentially encoded in the transition function. We have probabilities, TSAS prime. It's a big table, three-dimensional table in which we can look up the probability of every state action, next state triple. And then there's a reward associated with this transition. So that's one thing that's different from what we've seen so far in Expect2Max. In Expect2Max, there was no rewards on the transitions. They were all the way at the bottom of the tree. Your terminal nodes had utilities. Here, they're given along the way. That's really a minor tweak, though. You can imagine running Expect2Max just as well when there are rewards along the way. You just, as you pass numbers up, you accumulate the rewards you get along the way rather than just passing up what's coming from the bottom. So it's not that we're looking at MDPs because Expect2Max cannot handle rewards along the way. It's because what I said initially, it's because we want to solve problems where we act infinitely long and we want to deal with the repetition in this Expect2Max tree in an efficient way. And then 2 lectures from now, we'll also see how it allows us to do learning in these settings more readily than would be possible otherwise. So now we need to look at utilities of sequences. So what preferences should an agent have when there's a sequence of rewards? So rewards, more is better. That's the way we define them. So the utility of 2, 3, 4 should be better than the utility of 1, 2, 2 if you had a 3-step sequence. Then there's a question, do you want them now, the rewards, or later? Well, depends a little bit on who you are, I guess. It's part of the problem definition. But a lot of people would prefer to get the reward earlier, so prefer the right thing here, 1, 0, 0 over the 0, 0, 1. Why is that? Well, who knows? If you get things earlier, let's say the reward corresponded to money, maybe you could do something with it earlier and so forth. So usually it's better to get the rewards earlier. So it's reasonable to maximize the sum of rewards. It's reasonable to prefer early rewards rather than later rewards. It turns out that once you have those constraints, there's only one solution, which is to have the value of rewards decay exponentially. And so something right now might be worth 1. Then the next step, the same gem would be worth, so the same state effectively, or the same state action state transition would be worth gamma, which is your discount factor. If you encountered it after 2 steps, it would be worth gamma squared. And because gamma is between 0 and 1, gamma squared is lower than 1. And so things that come later are considered less favorable than things that come earlier. So what it looks like now in your expected max tree is that on these transitions, when you get rewards, you have a weighting at the top by 1, the next layer by gamma, next layer by gamma squared, and so forth. So if you had a discount of 0.5 and you had the utilities, you wanted to compute the utility of a reward sequence of 1, 2, 3, you'd have 1 times 1 plus 0.5 times 2 plus 0.25, which is gamma squared times 3, and that'd make for your utility value for that reward sequence, which would be which would be worse than a reward sequence of 3, 2, 1, where you'd get a weighting of 1 times 3 plus 0.5 times 2 plus 0.25 times 1. Okay, assuming our preferences are stationary, yes?
So, can you explain when you would use discounting as opposed to simply adding a penalty for each time step?
Okay, that's a good question. So the question here is, what's the difference between using discounting, where later things are less desirable than earlier things, versus adding a penalty for taking essentially time, every action. They have a very similar effect. So both of them will penalize taking a long time before you collect the rewards that you might really care about. One of the reasons to use the discounting is that it allows you to deal more readily mathematically with situations where you're going to be expected to act infinitely long. Because as what we'll see is that thanks to discounting, we can bound the total weighted sum of rewards that you could accumulate. And once that's bounded, it's much easier to work with than if you could end up accumulating an infinite amount of reward summed over time. So that's where discounting comes in often handier than delivering reward. Delivering reward can be useful at times because it might be easier for you to tweak that number than it might be to tweak the discount factor. In your project 3, you'll actually get to play with some of those numbers, and you'll see that they have a very similar effect in terms of how your policy will change. For example, the thing we looked at initially would change the living reward. We could have changed the discount factor. You would have seen a similar sequence of optimal policies as a function of how much you discount versus as a function of how much you penalize for living longer, so to say. So assuming you want to go with stationary preferences, what does that mean? Stationary preferences means that if you prefer reward sequence A1, A2, and so forth over reward sequence B1, B2, and so forth, then you would also prefer the reward sequence R followed by A1, A2, and so forth over the reward sequence R followed by B1, B2, and so forth. If this equivalence is true for every possible reward sequence, if you prefer one over the other, you can always add R, which is a fixed thing in front of both of them, and have the same preference still. That means you have stationary preferences. If you stick to stationary preferences, it turns out there's only one way you can define utilities in a rational way, which is shown over here. It's shown in 2 ways, but it's really the same thing. You can define them by summing your rewards or by having an exponentially weighted sum of rewards, but in the special case you said gamma equals 1, the second case reduces to the first one. Okay, so let's see if we have some intuition for how this plays out. Here's a little quiz. Here's a little grid world. from A and from E, there's only one action available. The policy is essentially fixed. You don't get to choose. You have to exit. The reward on exit will be 10 or 1, depending on which of those states you were in. For the middle states, you can choose between east or west. So let's see. What if gamma were equal to 1? What would the optimal policy look like in this grid? So for 3 states, we need to decide whether the best action is east or west. Over there.
Always want to go to the left.
So the answer was you always want to go to the left. Why is that? Well, that action brings you to the state where you can exit with a reward of 10. Yes, it takes longer to get to that 10 if you start from over here than it would take to get to the 1, but there's no discounting. Discount factor equal 1, so it's fine for it to take longer, and so you're going to be willing to take your time to get that higher reward. Now, what if gamma equals 0.1? Over here. So you want to go to the right from every possible state? Okay, so the answer here was you would want to go to the right. I'll interpret your answer as follows. You want to go to the right from here because you're very close to the 1. And if you had to go all the way left, you'd have a lot of discounts gamma multiplied together. And then, of course, from here, you'd still want to go to the 10 because it's closer to the 10 and 10 is better. From the middle, clearly it's better to go to the left because they're equally far. Now, whether this is the right decision here, we'd have to do a little bit of computation, of course. We have to check, is that indeed the right thing to do? We assume this is deterministic, so if we go to the right, then the next thing we do is take the exit action, so we get a reward of 0 on the first step. Then we get a reward of 1 on the next step, multiplied by gamma. Gamma is 0.1, so we end up with 0.1 total. If we go the other way, we'd end up with a 0 on the first transition, then a gamma times 0 on the next transition, which gets us here, then a gamma squared times 0 on the third transition, and then a gamma to the third times 10 on the last transition. And so that means if we went all the way left from over here, we'd end up with 0.1 to the third times 10, which is equal to 0.01. Which is worse than 0.1, so indeed moving right from over here was the right thing to do. Now, where are we ambivalent in terms of whether we want to go left or right from that particular state, D? Well, we already kind of wrote out the equations here. We said if we go left, the reward sequence we get is 0, then the next one is 0 again, discounted by gamma, next one is 0 discounted by gamma squared, next one is 10 discounted by gamma to the third, and we're equally happy going left or right from state D if that's equal to what would happen if we went right, which is 0 plus 1 times gamma. And now these zeros don't really matter, obviously. Then we have 10 times gamma to the third equals to gamma. Let's solve that, so that becomes 10 gamma squared equals 1. So gamma squared equals square root 1 over 10. Sorry, gamma equals square root 1 over 10 is when we would be wanting we would be equally happy going left or right. If gamma is smaller than that, meaning we discount very heavily, we'd go right from D. If gamma is bigger than that, which means we don't discount all that much, we'd go left and take the longer path. All right, so what if the game lasts forever? Will we end up with infinite rewards? Kind of talked about that a little bit in answer to an earlier question, but let's look at it in a little more detail. So if your game lasts forever, in principle, you could get a sum of rewards that's infinite, which would be difficult to deal with because now, which infinity do you prefer? This one way of getting infinity versus this other way of getting infinity? And it can get very tricky to find the optimal policy in these kinds of MDPs. So we'll look at cases where we don't have that problem. One way to avoid that problem is having a finite horizon. So this is similar to depth-limited search. You say it can only last so long in terms of how long we're going to act in this environment, so we only look that deep after capital T time steps, the game finishes. This could be really true. This could be actually your problem. It could be that you only care about capital T time steps. It could in many cases be an approximation where really you want to act much longer, but you make this approximation of only looking T steps deep. That's effectively what expected max would do. You would look T steps deep, you take your first action, and then once you see the outcome, you'd rerun your expected max search for T deep, take your first action, and repeat. So there is a way to work with something that only looks T deep that is pretty reasonable, but still it might not be the right thing because you are ignoring whatever is deeper than T, and if there's something interesting happening after T steps that you should take into account now, you'll completely ignore it. Okay. Now, one thing to note here is that the consequence of looking only T steps deep is now that your policy might depend on the time into your sequence of actions. So, for example, if there's very much time left, you might be willing to take the time to move towards a really good reward state, but if there's very little time left, you might just move to the closest by state where there is at least some reward to be collected. Discounting is the other solution. What happens when you discount? Even for an infinite sequence of rewards, you can write out the sum this way, sum over all times, reward at that time times gamma to the power t, will be bounded by the maximum reward you could get in any state, or for any state action state transition, divided by 1 minus gamma. What is that? Breaking this down here, really what we're saying is sum t equals 0 to infinity, gamma to the t rt is smaller than or equal to sum t equals 0 to infinity, gamma to the t r max, because r max is defined to be the maximum reward you could get anywhere in your MDP. Then this r max we can separate out. It doesn't really need to be multiplied in every time. It can be multiplied in once at the end. This here is a geometric series and is equal to 1 over 1 minus gamma. So we now know that our sum of rewards, once we discount, assuming gamma, of course, is smaller than 1, is bounded, and so we won't have to worry about infinite rewards. Another way to avoid infinite rewards is to set up your system such that it's guaranteed that at some point you will reach a terminal state. How can you guarantee this? Well, if your transitions are stochastic, then the noise in those transitions could be such that no matter what policy you follow, there's always some possibility that's non-zero that your next sequence of transitions will get you to the absorbing state. And if that is the case, and that is the case at all times, then over time, the longer you keep acting in that MDP, because at any given time it's possible that in the next several actions you'll end up in the absorbing state, those probabilities will add up, and ultimately you have a probability of 1 to end up in the absorbing state. So for MDPs where things are stochastic and there's enough noise, and you have an absorbing state and things are connected the right way, this will be true, and your expected, even though your actual sum of rewards in some cases could be infinite, your expected sum of rewards will still be finite, and the expected sum of rewards is what we'll care about because we want to maximize expected sum of rewards. Okay, so let's actually take a break here, and after the break let's recap what we just covered and start looking at how to solve these MDPs with something different than expected max. All right, let's restart. Let's restart and take a look at the results of the Project 1 mini contest. So what was the contest there? The contest presents you with a board. This board can be different on every run. If you're the blue AI, so to speak, your agents are sitting in the top right there. two ghosts on your own side. They can't really act like ghosts yet, but what they do on your own side is they essentially cannot eat any food pellets because they're ghosts. They have to run to the other side where they become Pac-Man. They can collect food pellets there, but to achieve a certain score, you actually need to bring those food pellets back to your own side. And so, in this case, the way the game is defined, you need to collect all but 2 of the food pellets, bring them back to your own side to win the game. Whoever does that first among the 2 teams wins the game. So what we did is we have a ELO ranking system where submissions get played against each other for many, many hours after the submission deadline to get the ranking to converge. And then we essentially look at the top ones and we'll go through them here in class. So there were 31 submissions. Let's first look at some of the fun names in the 11 through 31. Not the Staff, Smellybot, Dirtbot, version 3.2, and Neapolitan. One way to always get mentioned in lecture is to pick a cool name, so keep that in mind for next time. Now let's take a look at the top 10. At number 10, we have AYY Gent by Callie Wang and Ted Yuan. At 9, we have Doji 2.4 by Kai C and Denise Zeto. At 8, we have Manpack by Michael Tong. At 7, we have Chung Yen by Chung Yen. At 6, we have Mood 2 by Jeffrey Zhang. At 5, we have Tao by Jonathan Tao and Fabian Ho. At 4, we have Scrub Life by Michael Cheng. Congratulations to the top 10 minus 3. Now let's take a look at the top 3 in alphabetical order. We have Bull So Hard by Anthony Su and Peter Lee. D's Pac-Man by Shuheng Dai. And Knife Intensive by Dalen Yang and Ravi Tadinada. All right, are Anthony and Peter here? Let's see, can you raise your hand if you're somewhere here? You Anthony or Peter? Anthony? Anthony over there. Is Shuheng Dai here? Over here, okay. Dalen Yang and Ravi over there. Okay, so we have Knife Intensive down there. We have D's Pac-Man over there and Ball So Hard over there. Now the way we determine the ranking is by extensive play against all teams, not just a heads-up match between these 3, but we picked the heads-up matches between those 3 that are consistent with how the ranking came out, okay? So we'll start with looking at Bull So Hard versus D's Pac-Man. The loser of this will end up number 3, which is still pretty awesome. The winner of this will then be shown in a game against, what's the other one called? Knife Intensive for first place. So what's underneath Bull So Hard? They defined a greedy search problem that started from the first instantiated Pac-Man through all food dots, then back to the original Pac-Man position. After determining the output of this, iterated through all possible pairs of food dots to exclude from the given list. For each list created by removing these pairs of food dots, determined the best division of labor for dots to eat such that the 2 Pac-Men would return to their own side in the minimal max of the 2 paths that each Pac-Man traveled. Lastly, assign the first Pac-Man to run through his path forward and the other to run through his path backward. Then D's Pac-Man. Search problem is defined where each state is a tuple of number of moves made by Agent 1, position of Agent 1, number of moves made by Agent 2, position of Agent 2, current food grid. At each step, the agent that has made fewer moves would move to any of the remaining food, cost of 1 per move. Heuristic is the size of the minimal spanning tree of all but 2 of the remaining food pellets. Also subtracted the distance between the 2 agents so that states with agents further apart would be preferred. To avoid exponential blow-up of A-star search, limited the depth of the search where depth is defined as the number of food pellets eaten. The search would start with depth 0 and continue with higher depth until time is up. The team manager class handles the search, in particular to break the A-star search into two parts, initialize and search, so that the search can be paused and resume if needed. Okay, let's take a look at how this plays out. You can try to think about these two strategies and think who would likely be the winner here. Or think of those people if you know them and think who would likely be the winner. Where's the game? Okay. Ooh. More space. There we go. A little higher up somehow. Oh no. Oh, this is not working with me very nicely. Let me see. Here he is. Scroll down. Here we are. Barely fitting. Now play. So blue is These Pac-Man, red is Ball So Hard. So both are eating the food pellets pretty quickly. Now they got to get back. And blue gets back just a little earlier, even though red also ate all the food pellets, or enough of them, but didn't make it back as soon. So we have going on to the match for first place, These Pac-Man, and we have Ball So Hard in third place. Let's take a look at the matchup between these two. So let's see. Oh, the name is wrong there. Should be knife. Should be called knife something on the left. So what's going on with the team on the left? Phase 1, which is 15 seconds for 2 agents, 30 seconds. Find contiguous groups of pellets. Random restart hill climb with a configuration scoring function to separate clusters into 2 partitions, 1 per Pac-Man. So they're going to split the board into responsibilities for each Pac-Man. Second phase, when it's running, go to closest pallet. A-star search with maze distance heuristic. To eat the pallets each turn, search path for all with A-star, meaning for all pallets. Inadmissible heuristic, distances to the closest pallet plus distance from that pallet to the next closest, and so forth. If one Pac-Man finishes early, helps the other by going to closest pallet in the other's partition, and head home once n-2 pallets collected, using A-star search to find the quickest path home. So let's take a look at how this plays out for first place. So left, knife intensive, right, These Pac-Man. Very, very close. Just, if there just weren't that wall there to get back, would have been a tie, potentially. But so These Pac-Man actually wins the contest. Knife Intensive comes in second. So at 3, we have Balso, Hart, Anthony, Sue, and Peter Lee. At 2, we have Knife Intensive, Dylan Yang and Ravi Kadinada. And at 1, we have These Pac-Man by Shuheng Dai. Just taking a picture of this. Okay, so it's our top 10. Just want to say congratulations to everybody who participated. 31 teams is great. One thing you'll see as the class progresses, actually we'll build on top of this contest. And that you participated now will help you in the next one and that you already have a head start. But if you haven't yet, I'd strongly encourage you to jump in on the next one because there will be essentially 3 of these and they'll all kind of be extensions of each other. After project 2, the mini contest there will be adversarial in the sense that now on your own side, you will be a ghost that can eat the other Pac-Man that come and eat the food pellets on your side. So you're literally playing against each other, not against time, as it was in the first one. There will be power pellets and so forth to kind of make the game more interesting. And from there, we'll build onto it. After project 4, we'll actually have add-on special powers that you can only noisily observe, and you have to run probabilistic reasoning to figure out what kind of special powers the other person might have and so forth. So I strongly encourage you to start looking at this. We explicitly make the contest due well after the project is due, such that you can use all your time for the project you want, and there's still some time left to work on the contest if you want. All right, any questions about the contest? Okay, then let's go back to lecture slides. And let's recap MDPs. Okay, what was an MDP? It was this thing that we used to define or formalize a stochastic search problem where consequences of your actions are non-deterministic. There's a set of states, which we've seen in many formalizations now. There's a start state, there's a set of actions, there's a transition model which tells you, given current state and action, what's the probability in landing in next state S prime? And then there's a reward associated with each state action state transition. And there could be a discount gamma, which discounts rewards you get into the future, because gamma is smaller than 1 typically. Things you get in the future are valued less than things you get earlier on. In terms of expect-to-max, this is what it looks like in an expect-to-max tree, where you start in some state that's a maximizer node. You might choose from a set of actions. Once you commit to that action, you hit a chance node. Then chance will decide what the actual outcome is of that action, any of these following states. And on that transition here, you will also receive a reward, which might be discounted depending on whether you have a discount factor or not. The utility is the sum of discounted rewards, and the policy, which is what we're after, prescribes for every possible state what the right action is to take. So we're interested in finding these policies. We know what a policy is, we just don't know yet how to find the optimal policy, the one that maximizes expected sum of discounted rewards. Okay, so we'll define a little bit of new terminology here. We'll define the value or the utility of a state, which is associated with these kind of maximizer nodes, as the expected utility starting. Let's see if we can get rid of this at the bottom here. Apparently not. There it is. Okay. So the value of a state is the expected utility when you start in a state and act optimally from then onwards. Even though we don't know yet what it means to act optimally, we can define, if you were to act optimally, what would be your expected sum of discounted rewards, and that's V star of S. Then Q states are the states that we refer to in these chance nodes. And so the Q value of a Q state SA is the expected utility when you start out from this Q state, which means you are in state S, committed to action A, you don't know yet what the outcome is of taking that action, but if going forward, action A you've committed to, can't change that anymore, but any future action would be optimal, the expected sum of rewards you'd get doing so is Q star SA. Then the optimal policy pi star is the one that prescribes optimal actions in each state. Okay? So let's take a look at what this looks like in our grid world. So don't worry about this so far. It says number of iterations that it takes to compute something like this. That'll matter later. But for now, let's look at the numbers. So what do we have here? The value here is 1. Does that make sense? Let's look at the settings. There is some noise, 20% chance of noisy action. There is a 0.9 discount factor and a living reward of 0. Then this value of here is saying that if you act optimally from that state onwards, your sum of discount rewards will be 1. That makes sense because all you can do from there is take the exit action. You're done, and you get a reward of 1, and it's happening right there, so it's not discounted because it's happening in the first time step if you start from there. How about this one over here? Similarly, in the pit, only 1 action, reward of -1. And so the optimal thing that can happen from there is just get that -1. Now, how about over here? You're 1 away from the state that you want to get to then collect a reward, 0.85. Does that make sense? Why is it not, let's say, 0.9 times 1? Because you'd hope for, in the second step, getting your reward, and then it would be discounted by gamma, 0.9 times 1, over there. Exactly, there's a chance that when you're here, even though you try to go to the right, you end up going down or you end up staying in place, in which case you'll reach that exit state with a reward of +1 later. The reward will be discounted more because it's later, and so on average, the utility from that state that you get is 0.85. And so we can work through all of these and think about why it makes sense. The further you're away from this state, the more the value will decrease because it takes longer to get there. And then, of course, if you're taking the up action here, there's a chance that you actually move off to the side, fall in the pit, which would be bad, and so it doesn't have as good a value here compared to over here. Now, these are the V values associated with states. We can look at the same grid and look at Q values. So now for each state, there are typically 4 actions in this case, or only 1 if you're in an exit state, so these 2 over here are special. The other ones have 4 actions. And so you can see here that the 0.85 that we had on the previous slide is still here. It's associated with if your action is to move right. But for any of the other actions, the Q value will be lower because it means that you're committing to a different action. And resultingly, the sum of discounted rewards on average will be less than if you took the correct action. And you'll see that for every one of those squares. So let's look over here again. The best thing over here is the 0.57. That's the same as the 0.57 over here. So the value every time in a state is the highest of those Q values. It's the expected utility for that Q value or Q state that is the best among your choices. Okay, so that makes sense, of course, because the values are sitting over here, the Q states are sitting over here, and you have a maximization step there, so you can take the maximum over Q values to get your value of your state. So this is a recursive definition. Sometimes we're saying that the value in a state is the max over Q values of its successors. And then for the Q values, we can write out a similar equation, which says that the Q values are a weighted sum, weighted by the probability of achieving those next states as prime, of the reward you would get for that transition, plus a discount factor gamma times the utility you get from that next state onwards. So this thing here, V star S prime, is saying the optimal you can get on expectation from S prime is encoded right in here, and that from this Q state here would summarize essentially this entire subtree here, right? That's the value that's sitting right there. Now, because it's happening later, it gets discounted by gamma, so you have gamma times V star of S prime. You can combine these equations, and now we have an equation that tells us what V star is for every state, but unfortunately as a function of V star at other states, and so since we don't know yet V star at the other states, we're still a little bit stuck here. It doesn't just tell us right away how to get the value out. But we do have a set of equations here. If we were to solve that set of equations for values, where keep in mind this V star will be some kind of vector with an entry for every state. This will be, if there's, let's say, 100 states, this will be 100 equations, 100 unknown values, and you can in principle solve this nonlinear system to find the values that satisfy the set of equations. So in principle, we have something we can do. Okay, so let's look at this racing search tree. What's going on here? This is what it looks like with a short horizon, but if we are thinking infinite horizons, it actually keeps expanding and expanding. What we can do now is look at values in this search tree. First thing to observe is that we're doing way too much work if we run expect-to-max. Why is that? States are repeated many, many times, right? So what's sitting over here, this entire subtree is the same as this subtree, is the same as this subtree, same as this subtree, and so forth. And this is happening in many, many places where the subtree below is the same in one place as it is in another place. So expect-to-max would not exploit this and would just repeatedly compute the values of those states, even though it's going to be the same. Another problem is if you run naive expect-to-max, your tree goes on forever, so you go depth first, and you'd never return because it just keeps going deeper and deeper and deeper. Now, intuitively, you shouldn't need to go super, super deep because things that are deeper get discounted more and more. So you get a discount of 1 here, but then gamma here, gamma squared here, and so forth. And at some point, you get gamma to some large number n. If n is very large, gamma to the n will be very small, and what happens below there is not really all that influential anymore because it adds up to almost nothing, right? So there's some intuition there that we don't really need to do infinite computation to get out something good. But expect-to-max would run to the bottom, and that would be it. So let's first look at limiting the values, not go all the way to the bottom. So time-limited values, Vk, are the optimal values for state S if the game ends in k more time steps. So remember, we had V star before. V star was for essentially k equals infinity. So V star is the same as V infinity in the notation we're using up here. But right now we'll let k be something else than infinity. So the value of Vk of a state is the same thing as if you were to run a depth k expect-to-max search, you'd get back a value. That value is what we're after here. So we actually know how to compute this. We know how to compute Vk of S for every state running expect-to-max. So you could set up a tree, you could limit your depth, you could compute each of these Vk values. So let's take a look at what these values look like on the slides, because it's a little easier to display them that way. So if you only look 0 steps into the future, k equals 0, then nothing happens. V0 is 0 everywhere. Once you want to take 1 step in your game, the depth 1 values are shown here. And the only place they're non-zero is places where within 1 step you would accumulate a non-zero reward. Then if you're looking too deep, this is what the values look like. This is what we're looking at here is V2. Why is this still 0 here? Well, if you look 2 steps deep, sure, you could get some kind of negative thing happening to you, but if you take the right action, which is actually not shown here, you should take the sideways action, you will always avoid that negative reward. And so even though there is a possibility in principle, the optimal thing would not encounter any reward, and so you'd still be at 0. As we go along, we see how these things propagate out from where the rewards are to other states. If there were a living reward that's non-zero, then for all of these, even V1 would be non-zero. But because here we don't have a non-zero living reward, most states the reward is 0, things propagate out in kind of a wave pattern from where rewards are given out to other places. So this is what you see happen. As k increases, you see these values start changing less and less and less. Why? Because of the discounting. And so if you go deeper and deeper in the tree, these bottom things contribute less and less and less, so that extra refinement is not changing much to these values here. And here's k equal 100, which is almost identical to k equals 12, only a minor one-digit change in that entire picture. So what are we doing here if we compute time-limited values? Here's what the picture looks like. We would start, if ultimately we're interested in depth 4, which is shown over here, we would start with computing the bottom values here, but there's a lot of repetition. We shouldn't compute values for all of those. We should just look at one time the cool state, one time the warm state, and one time the overheated state, and not repeatedly look at them. So we'll have a way to do that. Just do 3 computations in the bottom layer. Once we've done that, we can look at one layer up. Same thing there. It doesn't matter in which branch of the tree you are. If you're in the cool state and there is one step left, the history doesn't affect the value you get, that is the expected sum of future rewards, once you know you're in the cool state. Same for once you know you're in the warm state, once you know you're in the overheated state. So we only need to consider each state once in this layer. Same thing for the layer above. Each state needs to be considered only once in that layer, because the values will be the same. And same thing for the layer above. And at the top, in principle, we could consider all if we don't know where we're starting. In this case, if we know where we're starting, we could just consider the cool state. And so you could see here that, in principle, we could run expect the max depth 0 to compute this over here, then an expect the max depth 1, so to say, to compute these values, but for each one of them only once, and work our way up to the top, where we would consider each state only once in each layer. So how do we do this in math? So here's the value iteration algorithm. We start with setting V0 for all states equal to 0, because when there's no time left, no rewards will be accumulated. Then, given we already have Vk for some k, we can do one ply of expect-a-max, which we know how to do to compute Vk plus 1. So Vk is used over here. It's the value of the next state S prime with only k steps left, and that's all we need to be able to compute Vk plus 1. So let's look at this equation over here. This is the key equation we'll be looking at essentially the rest of today and the next 3 lectures. So what's this doing? It's saying Vk plus 1 is the max over a set of possible actions over here of once you then took an action, you need to average over possible outcomes. It's a weighted average depending on how likely each outcome S prime was, and then the values sitting at these outcome states S prime are Vk S prime. That value is if from there on, if you started there and had k times to act, but you're only going to get there one step later, so everything that you get from there needs to be discounted by gamma. So there's a gamma up front here. And then for the transition itself, there's a reward which is over here in the equation. So that's our expect-a-max update equation effectively that tells us how to go from Vk to Vk plus 1 for all states. Then we repeat this until this converges. I haven't shown this converges, but we'll look at that later. The complexity of each iteration is order number of states squared times number of actions. Then the number of times you need to do an iteration depends on how deep you want to go, which value of k you want to compute this for. But overall, it'll be k times s squared times a, which is not exponential in the depth anymore. It grows with the number of states that you have, squared with the number of states, but not exponential in the depth of the tree. There's a theorem here that says that this is guaranteed to converge to unique optimal values. This assumes that the expected sum of rewards is finite for all states. So if one of these conditions that we talked about earlier holds true, the simplest condition being gamma lies between 0 and 1. It is also true that the policy might reach its converged values long before the values achieve their converged values. And there's something we'll exploit there in next lecture. So let's look at an example of this in action. So value iteration for our car example. This is the equation we'll be using. Initializing all values equal to 0. Then to go one step up, we want the value here for the cool state. Well, from cool we could take two actions. We need to consider both. So to compute this value over here, we need to do two calculations. The first calculation is if from the cool state we were to take the slow action, which would result in a reward of +1, and we would be guaranteed to land back in the cool state. So if we did this, the first calculation gives us +1 plus gamma times the value v0 of the cool state, which is 0, and so this is equal to 1. The other action is to take the fast action. If we took the fast action, well, there's a 50% chance we end up warm, a 50% chance we end up cool. So now we have a computation that is 0.5 times one situation plus 0.5 times the other situation. In the first case, we end up cool. The reward is +2 here, plus gamma times the value v0 for cool. The second case, fast action, we get a reward of +2, plus then gamma times the value v0 of the warm state. This is equal to, well, the values at v0 are all 0, so this is, if we calculate it out, it's equal to 2. This is 1. Between 2 and 1, the 2 is better, so the value over here is 2. We can repeat this for all other states. The same thing. To compute the value, we consider all possible actions, compute the expected value of taking that action in that state using this expect to max update and fill them out. So let's do that. Fill them all in. All zeros at the bottom. Then we have 2, 1, 0, the next layer, and 3.5, 2.5, and 0 at the top layer. All right, so this is algorithmically how things work out. Let's now take a look at why this actually is guaranteed to work for us. So the claim that we had is that if we let k increase, we keep doing this, go from v0 to v1 to v2 and so forth, keep going, these values will converge. Okay? So there are a couple of scenarios. If the tree has a maximum depth, at that point things stop. It's of course going to converge because everything is going to be a finite sum of finite things, and so it'll be finite and it'll converge. It'll be just the truncated values. So that's an easy case, but we'll use it as a starting point to prove what we're interested in. So if the discount is less than 1, let's consider two scenarios here. We're looking at the same game tree, but in one scenario we compute vk, the other scenario we compute vk plus 1. What's the difference in that computation? When we compute vk plus 1, we include the last layer here in the computation. We compute, if this is layer k plus 1, we compute the expected max value for this entire tree. If instead we were to compute vk, what we are doing effectively is we are taking these transitions here, and for those, set the reward equal to 0, and then effectively what happens is we're only looking k deep because what happens from in step k plus 1 is 0 anyway. So the approximation we're making going from k plus 1 to k is zeroing out the rewards you obtain in the very last step. Okay? Well, let's think about what those rewards could be. Let's assume there's some worst case reward, R-min, some best case reward, R-max. We can look at the max absolute value, and we know that the contribution of what's happening in that last layer, while it's all 0 here, the contribution over here to the top value could be at most gamma to the k times max r. So that's the biggest error we might make in our calculation of the value at the top. Now, as k gets larger and larger and larger, this worst case error we might be making at the top will converge to 0. And so what we see here is that as we grow k, the difference between k and k plus 1 will go to 0. You can actually show it goes to 0 quickly enough that ultimately things converge to the value that you would get if k were equal to infinity. And you'll get pretty close to that even with k's that are fairly reasonable. What do I mean with reasonable? Let's say your discount factor is maybe 0.9, then something like 100, k equal 100 will get you very, very close to what you would get for k equal to infinity. But the main intuition here is what's happening down here is that between k plus 1 and k, the only difference is that the bottom gets zeroed out, and that bottom contribution can be at most gamma to the k times the max absolute value of the reward. All right, that's it for today. Next time we'll look at methods that directly try to compute the policy.